No, it's two. Is it plus?
Two, right?
Two. So I guess I could kind of like stick a third one in here. And then. Have four frequencies.
Everyone did the same. Why am I thinking wrong? It's wrong. Yeah. Okay. Okay, most of you got this wrong, but I think you will see this again in the homework. Manupta seems to have got it for fasting. Okay, so I think you have to do 4 pieces. I think that's a. So the first of all homeworks. The homework 8 posted. 8, right? No?
Homework 7 is due today or next day?
Up to you guys. It is officially due today, but take it Thursday.
Okay.
Reasonable. Like,
Thursday is right.
in general, I think you all have been good with submission of homework. So as far as you unanimously agree that you want it due another day, that's perfectly okay.
For this, I think we need like a 1 day, one of.
That's okay.
Innovation.
And I posted it late, so you can blame it on me. I posted it late, so that's okay. But the key point is I keep coming up with new homeworks. I don't wait. Right, so the class doesn't get delayed. So you do it at your own pace. I would say don't delay too much. Like after a while, it gets, there is no time, right? 16 weeks, the final line, our final deadline doesn't move. So finish it off. I would say these 2 homeworks before the midterm, but we have a midterm, correct? Homework 8 is April 2, midterm 2 is April 4. So let's say this is the final deadline for all the homeworks before midterm. That's reasonable to push you guys. Anyway, your work for the exam is everything is covered. Is that reasonable? Yeah. Otherwise, in general, whenever you guys unanimously say that no, we are not able to do the homework, I'll accept it. Okay, so. There's also, I thought I should say solar eclipse. Anyone knows what's the time for the solar eclipse?
2 o'clock. is
Yeah,
whenever it happens.
so
2 p.m.
total solar eclipse happens 1:09 p.m., like 2 p.m. and plus or minus 2 minutes. It's for 4 minutes or 4 minutes and
We have to fix that.
on April 8th. Monday, classes are closed, university stays open. And 2 minutes plus or minus, but partial solar eclipse is the same, this is a peak, but it starts 1 hour and 15 minutes before and minus 1 hour and 15 minutes, right? That means about 12:30, 12:45, it begins. Partial solar eclipse is not visible with naked eye, so you will need glasses, eclipse glasses, for that. Otherwise, if you make a hole on a sheet of paper, you can see an image of the sun being blocked by the moon. In the image, so it's kind of nice images. Often you don't even need a hole in a paper. Sometimes trees, if you're underneath a tree, there are all these small holes that are formed. So you will see the shadows are all, instead of circular, they will all be half moon shaped. So it's kind of nice, and find a suitable spot. I think the things to look for from what I remember last time is stars will show up. At least 1 or 2 stars will show up. If there is a planet close by, they will show up. It gets darker, significantly darker. So it will be almost like,
To the birds roosting.
yeah, and birds will start chirping. That depends on where you are. If you're in the stadium, probably you won't hear the birds because there will be so many people. But if you're in a quiet place, you will should have. And this time apparently, have you heard of cicadas?
Yeah, yeah.
They are supposed to be coming out. That these are insects which come out. At least they have a periodicity of 7 years or no, 13 years or 17 years, correct? So they come once in 13 years or so, and they are supposed to come now. Anytime the ground temperature is 65 degree Fahrenheit. And
The woods
If-
gets noisy too.
and if they come at the same time, so there will be all these insects and how they behave. So those are sort of interesting things. It doesn't happen often, like I think in someone's life, usually this happens only once or twice. Usually once, and sometimes you may not have a solar eclipse at all. These days, there is so much mobility. It seems like it is more often, but it's not that easy to have a solar eclipse coincide with where you are. So yeah, use the opportunity. And what else can I think of saying? Oh, demonstration, yeah, that is us. Yeah, yeah, so some of us, I think we will be doing a demonstration in the.
Eighth bend down.
On both 7th and 8th. You don't have to be there. Some volunteers did sign up, so they have. And Manuka is going to be the main in charge. Or at least if something happens, I blame on you. I mean, you're the person who thinks about what is to be done, and of course, others will help you. So I will also help. And yeah, I would be there. I think the main point is that, yeah, me and Manuka and some of us who volunteered will be there in the arena. There are some demonstrations. There will be a lot of people coming in and try to show physics demonstrations. But I will also encourage that if you're not if you do not have any commitments, we have Giant City Park here. It gets quieter there. Might be nice. It depends if you like people, if you're doing this with people, that's also good.
Can you observe?
Can you observe?
The giants?
There are lots of open spaces there, yeah, and we also have, last time what we did was, one of us, April Henley, she had a telescope. We put the telescope in the apartment complex itself. A big ground kind of area, and it was nice, and people came and started using it, so. You need a filter, if you're using a telescope, usually it's easily available. And then you can take pictures, what else, I'm thinking, what else happens during that time? Yeah, I think we covered that, that's what that comes to my mind.
I think we can use the telescope from the top of the building.
Yeah, I'm pretty sure there might be some observation happening on Nectar's roof that might be there, and we also have a dark side, if you're aware of this, or do you know what a dark side is? I think Nanida, you know?
Yeah, they usually go, but I didn't.
Yeah, so it is slightly outside the campus or at the edge of the campus. It is a darker, relatively darker region. So they plan to do some experiments there, I'm pretty sure. I don't know what other activities going on, so involved.
They went there. They're
Other-
still working there,
Still,
working at that side.
who?
So the group.
Oh, the group is still, okay, yeah, so approach Tanita, yeah, she will tell you, or Bob or Corey. Yeah, they should tell you, what are so a lot of options there, but gotta have some orientation. On that day, it might get crowded at the last moment, so be prepared. At the last moment, you may not be able to do things. Traffic might be too much, it may not be controlled, may not be easy to. Again, it depends on number of people who show.
It's a crowd. I heard the other university also coming in.
Yeah, lots of people would be there, a lot of important people would be there. This is, they use it to organize conferences because a lot of people are interested in coming in, so at least last time when this happened, we had a lot of mathematicians come, and there was a small conference organized from the previous day, and then they watched the eclipse and return. But all that depends on where they decide to go, what's the weather prediction. So many people cancel at the last moment because if the weather is going to be bad here, so they will prefer to go somewhere else, which is understandable. And many of the people also go by the amount of time the eclipse is. Here it is 4 minutes and 10 seconds. In Texas, it is 4 minutes and 30 seconds, or maybe 25 seconds. So when you just go by the time, and if you want to pick a spot, many would pick Texas. So that's another a reason why many people might go to Texas. But either
We can
way,
take the picture from the normal camera, or we.
yeah. So if you have normal, it may not. If you just take it from here, you may not have it. Like you may not be able to zoom in that well. Try it out. The best is if you have a telescope. Put it on the eyepiece of the telescope, it comes out really nice. And what I suggest is that requires a lot of stability. You will have to
Very stable.
stable, but take a video. What I've seen is, this is what I see students doing. They take a video of that whole thing, and in the video capture the image, and whenever it is stable.
Problem is telescope then, we didn't have telescope, how can we reach the telescope? Because that may
There
be
is
the
one
problem.
with April Henley.
Mhm.
Ask her what she's doing or go with her. She has a telescope which is in my place, my house, but ask her or ask the department, they have a telescope. But they won't give it to you unless you have experience in it. Apparently, again, Nahida is involved in this. There's a lot of activities going on. Get involved, and that is
Because it's just 4 minutes, that's why there may be crowded, and you cannot get the time to look at from the telescope if the crowd.
Yes, that's true. During the eclipse, I would say, don't go for the telescope, just look at look at the sun, that is the best. And there is a lot of phenomena that happens around it. As I said, look for the star, look for the darkness, look for the birds.
But that we need to have someone who knows that already, otherwise we may not feel that.
I mean, for all you know, you might be the one who is telling it to others. You are the local expert here. I mean, trust me, like you are the physicist around. So you will be the local expert. You will be surprised how much you know more than others. So in that crowd that you will be around, probably you will be the expert. So, and if you read a little bit, you know more than a lot of them. Like, it's not that I know too much about Flux, I just know by reading and experience 1 or 2 Flux. So, yeah, that's mine. Thank you. Suggestion on solar eclipse, and we have half an hour. Okay. So, we have done stationary action principle or functional derivative. And we have used that to a great extent in understanding Newton's laws, right? That is all we did in the 10 weeks now. We learned the technique of functional derivative and used that idea, said there is a stationary action principle. And we have been able to redo many of the problems we typically do in using Newton's laws. But if you remember, most of the time we kept the variations at the boundary 0. Like, we did not vary the boundary. Now we want to come back and say that what happens if you vary the boundary? And we will learn that there's a lot more physics in that, lot more richness in that. So this is stationary action principle. With variation at boundaries. And I want to go a little slower when we hurried the Hamiltonian description earlier. So I'll at this point, and we have been doing this for quite some time. So no harm in reviewing a bit. Let's go back and do this using the first principles, not using the idea of just the functional derivative itself. Let's have the action in principle or action described in terms of the Lagrangian. And what does action depend on? When you write this as a Lagrangian? Let me write. What does this depend on? For you?
On position, velocity, time.
So this is R as a function of time. This is velocity. And this is time, right? So what does this depend on? This is a functional of what?
Position.
Functional of position and time, good. And it is not this time, this is a dummy variable, T1 and T2, right? It does not depend on velocity. Like velocity, it depends on through position. It is the time derivative of position. So as far as functional goes, it is only R. If you write it in terms of the Hamiltonian, then it depends on R and P. So we'll do that in a minute or a few minutes. Certain things to take care of or have a feel for. This R here or this time dependence in here, even though I write it strictly, I'm not supposed to write that. There is no explicit time dependence in a position. This is implicit. Okay. And this is explicit. And what does it mean by explicit and implicit? Of course, as a function, we all learn the explicit and implicit dependence. But at a practical level, whenever you take partial derivative, there is a difference between partial derivative and total derivative. Partial derivative hits only explicit time. total time derivative hits both implicit and explicit. Okay, that's the difference. We will be working here with both total derivative and partial derivative, and partial derivative hits only explicit, total derivative hits both implicit and explicit. Let's pretend, let's remind ourselves, this is recall, like this is review sort of, let variations at the boundary be zero, right? So that means delta of R at T1 is equal to zero, and delta of R at T2 is equal to zero. So this is going back to no variations at the boundary. Okay. So we are having the idea that there is a function. This is your at some time T1, that is, so this is T2, this is T1. And we make all these variations, but at the boundary, there is no variation. So at the boundary, we don't make any change. So this is what this means, delta R is zero, that means we don't make that change at all. And how do we calculate the change? So quickly, so the change in the action due to the change in the position, in this case, there is only one variable that we are changing. If it was a Hamiltonian, there will be two. I'll do that in a minute. So there is only one variable we are changing. So this will be W of action evaluated at R plus delta R, T1, T2, minus of R T1, T2. So evaluate this at a small change and then subtract it out. And we learn here that this is the same as T1, T2, T, and this is a function evaluated at R plus delta R, and d by dt R plus delta R on T, and then subtract the quantity out. Like hopefully this is got familiar by now, right? We have done this few number of times, so hopefully this is more familiar, right? This is an expansion. Remember, f of x plus a minus of f of x is equal to, as a series, how much is that equal to?
X plus zero to X.
What is this equal to? As a series, it will be a series. Taylor, expand this and then subtract out a. What do you get?
A,
Good. And function. Very good. Right. You said something.
Vilash.
Oh, Dilashi said something. Dilashi?
Delta.
Yeah.
That's something that goes to zero at the boundary.
Correct. So it is partial derivative, or in this case, it doesn't matter. You evaluate this at x, but I don't have to because it's already evaluated at x, right? So this is f of x at x plus higher orders plus order a square, right? So that's our understanding of Taylor series. Here there are two expansions. you'd expand this for delta R and the velocity term. So this is equal to T one to T2 dt. A is in this case delta R. And since it's a vector, I have to take a dot product. And instead of d by dx, it's a gradient that comes in, which I will write it as d by dr of the Lagrangian itself. Okay. And the next term here is plus. Notice dr by dt is one term, d by dt, that's your second term here. So this is d by dt of delta r. That's a vector dotted with this time velocity, right? Velocity, whenever I write velocity, it means it's just a short form for this, not a variable as such. That's it. Right, is that clear? Any questions on that? Any questions on this? Like, so I expanded one, so if there are two variables, you expand both, right? You gotta expand this, you gotta expand that. So that's your A times derivative, another thing with derivative. But I would like to isolate the delta R on to the left if I want to use the delta function, or we use the idea of delta function itself, right? When we take the functional derivative in here, I can use the delta function. So if I want to isolate that delta R, I integrate by parts in this, and I get T1 to T2, T. Now let's go to that's this term. And here I change the derivative from here to there. That's integration by parts. And there is a whole surface term that contributes. But then that is equal to 0 because the integrals are 0. If you remember that delta function that shows up. So this is equal to minus of delta R dotted with d by dt of dl dv. And if you want plus d by dt, the surface term here is delta R dotted with dl by dv. dl by dv, let me write it as p. But then this is 0 at the boundary, right? Also, it's an integral, sorry. Yeah, I did write that. So maybe plus. Right. And we say that this is equal to 0 at the boundary. This delta R at T1 and delta R at T2 evaluated here. So this is equal to 0 because delta R at T1 is equal to 0. Delta R at T2 is equal to 0. Right. That gives you a hint of what happens if you include the boundaries. If you include the variation of the boundaries, this won't be 0 anymore. Right, that is going to be the difference. Right, and that's what we will try to capture. If this was 0, that is what we have been saying. If that was 0, then if delta, the change in the action has to be 0, that means the stationary action principle, then whatever is inside has to be true. You would say this is dl by dr minus d by dt of dl by dv is equal to 0, which basically says that dp by dt, where p is Where did I write P? Where did I write P? Momentum is the derivative of the Lagrangian with velocity, that's equal to. And that gives you an idea of what force is going to be, right? Force, any kind of generalized force is the gradient of the Lagrangian. So derivative of the Lagrangian with a generalized coordinate is the rate of change of momentum with respect to the momentum associated with the generalized coordinate. So that's the idea. Question?
Here, how do you found double L or double V? The velocity.
This one?
Yeah.
Because, okay, so here. This quantity in here, this is dr by dt plus d by dt of dr. Right? So that's V. Right, maybe I should write it down here. So f of x plus a, y plus b is equal or minus of f of x comma y is equal to a times df by dx plus b times df by dy. Okay, so that's the relation. That's a Taylor expansion to the leading order. And now what we have is Lagrangian of r plus delta r. And this one is V plus d by dt of delta r. Right, that's the functional form we have. So minus of L R comma V comma T. Right, so use the same idea. So then now except I generalize this is all one dimensional, make it three-dimensional, and this is R or delta R dotted with plus. This is the variation, so d by dt. You should specifically write dr by dt, but that's too much clutter there. That's just to simplify the writing. That's a basic thing. Derive this with. I show somewhere, not that, let me make it simple. F of x plus a minus f of x is equal to a times. Somewhere in calculus, you studied this. Okay. Prove this. It's hard in the sense you have to assume what you know. Yeah. So, prove that. Using basic principles. Okay, so that's the Lagrangian. This is called the Euler-Lagrange equation. Right? Rate of change of momentum, where momentum is this, is equal to the force, generalized force. This will be the, so this is the generalized force. And that's generalized momentum. So same idea as Newton's law, it's just much more general. Rate of change of momentum with time is equal to the force. Okay. Okay, so we want to do the same thing with Hamiltonian. Before we go and do this, and I kind of pointed out what is going to happen, right? This is basically what is going to show up in the new way, but we want to do this more formally. That's the main idea, because we didn't really make the variations at the boundary, but still we see this form there, and it will be pretty much the same things that will show up. So, but before that, Hamiltonian formalism. Or Hamiltonian, that's it. Right. Instead of writing the action in terms of the Lagrangian, I can write the action in terms of the Hamiltonian. And remember, how is the Hamiltonian defined? Anyone?
V times. Momentum times. Dot product with V.
B dot P minus.
V dotted with P minus L. Right, which means L is P dotted with P minus H. Right. So the same action, if I want to work with Hamiltonian, just replace the Lagrangian with P dot with P. So my action now, new action is going to be, I'm not writing this here. So give me, leave some space here if you're writing. This is dt. T1 to T2. That's a Lagrangian, but I don't want to write the Lagrangian. I want to write the Lagrangian as this. So it is V, where V dotted with P minus of H of R, T and T. Remember, why don't we have the velocity here? Hamiltonian does not depend on the velocity. It is all, if you take the derivative of the Hamiltonian with velocity, it will come out 0. Like you can show that here. I think it was a homework, or maybe we did it in the class, that if you take the derivative of h with respect to velocity here, then it will come out to be 0. That means it does not depend on it. There is no dependence in it. I want to get rid of this velocity dependence also, so explicitly I write this as dr by dt. So this quantity depends on r and p. Here also p and r. So my action is now no more r dependent alone, there is a t dependence also. And it can depend on t1 and t2 also, because these two are not functional dependencies, these are functions. These r and p are functionals. I can change my r. So in that sense, this action is entirely different from the other action. Okay, there's a significant difference between the two. Here there is only r dependence, here there is a r and p dependence. So it's in terms of the outcome. So if I want to again write, get my action principle, I expand this again, right? Change the action equal to P plus delta P. Then T1 and T2 remains the same, so I'm going to leave it alone. So let me not be lazy. Find it. Minus. So wherever I see an R, I replace it with R plus delta R. Wherever I see a P, replace it with P plus R delta P. So that's equal to, start with that. This is T1, T2, T. This term, after I substitute it and then subtract it in here, so there are 4 terms. So let's do this dr by dt with P, right? When I put in R plus delta R, got it, with P plus delta P. And then I have to subtract out minus dr by dt dotted with P. So the first term cancels out, and the next term is dr by dt times P, so that's dr by dt times variation and P, and then I have plus P by dt delta R dotted with P. Right. And the next term is higher order. This is delta square, like there are 2 terms in that. Otherwise, it's order square maybe, say delta square. So order square. There are two variations in that piece, so that doesn't contradict. Is that clear what I mean by that? So that's second order term in that. So that's that piece that shows up. So I'm going to write that immediately in here. So this is dr by dt dotted with delta p plus and then the Hamiltonian, which has to be r plus delta r, t plus delta p, t and subtracted, but now this becomes plus, right? So it's plus h. That clear what's happening? So again, I can do the Taylor expansion here. I can write the leading order and get rid of that. So T1, T2, T1. I can write this the opposite way. And let me do this next step. Oh, let me do the integration by parts. So it is minus d by dt. No, sorry. Minus of delta r dotted with dp by dt plus the total derivative of delta rp. At these two is basically differentiation by parts. Instead of taking the derivative here, take the total derivative here, and then subtract out whatever was missing. In this case, here you have delta r dotted h by r minus of here is delta p dotted with h by p. Okay. This is the boundary term. This doesn't contribute if delta r at T1 is equal to 0, delta r at T2 is equal to 0. If things are 0 at the boundary, this term doesn't contribute. And what I have then is rearrange. Let me collect delta p first, maybe. Delta p with one and minus of plus delta r or minus one. So that's a variation in the action. That's I make a delta R variation and delta P, right? Hamiltonian has both position and momentum in it. So I make the variation in both. This is the variation due to momentum, this is a variation in position. So all that algebra is giving you that. Now we may go back to the stationary action principle. So stationary action principle states that delta change in the action is equal to 0 because of these two variations. If this is 0, how can we have this 0 for any arbitrary variation in delta and delta p? This should be 0. Each of this coefficient has to be 0. If for arbitrary variations, you need this to be true, this has to be equal to 0. Either these two are equal to 0, but then that's trivial, so we will say that this has to be arbitrary for any variation. I should be getting that, so in that case, this is equal to the coefficients has to be equal to 0, and that implies that dr by dt is equal to the derivative of the Hamiltonian with t, and the second equation is dp by dt is equal these are called anyone? What are these called? Hamilton equations of momentum. Right. This is true even in quantum mechanics. Okay. So in quantum mechanics, just maybe give you a this also is equal to r comma h, and this will be I over h bar. H bar. This is equal to p comma h energy times, so I think h bar is down. I over dimensional. Yeah, dimensional should be. And we have not done this at all, but we will motivate this in the next 2 weeks or so. We will see this again. But this is what we have done. So that's extra. So quantum mechanics, Heisenberg's equations of motion. So this is the first equality is Hamilton equations of motion, which is true even in quantum mechanics. And these are Heisenberg equations of motion, equations of motions, which connect with the Hamilton equations of motions with that h bar in them. So in a way, commutators are nothing but the calculus. This is a derivative, right? Derivative is a calculus of the dynamics, if you want. And commutators are the calculus of dynamics. That means how does momentum change is decided by how does momentum change, right? The rate of change of momentum with time is decided by the commutator. I think of calculus but we'll do that. We will see that connection maybe 2 or 3 weeks down the line when we talk about Poisson brackets. Okay, that's pretty much Hamiltonian, but now we want to do this all over again with the variations at the boundary, and I want to go slow and see what other changes that comes in. So let's go back here and now lift this condition.
So
Yeah.
here, like when you take the action principle, how these two components become 0.
Oh, so okay, so this is 0, and we are saying for arbitrary variations in delta R and delta P. So we are saying that think of delta R times some A plus delta P times some B is equal to 0. But this is arbitrary. That means to say that I can put in a value here. So I put in R1 and P1. Right? That's equal to 0. But that doesn't specify because that's 2 unknowns, 1 equation. Put in another value. Delta R2 times A plus delta. That's what arbitrary means, right? I can put in any value I want. Now there are two equations, two unknowns, and they are zero, right? The only possibility is that A is equal to 0 and B is equal to 0. In fact, I can put in as many equations as I want to. So if I have an equation with arbitrary values associated with it, that means coefficients has to be equal to 0. Same thing with vectors, right? We do a vector A, there's AX in the I hat plus AY in the J hat direction. If this is equal to 0, then AX has to be 0, AY has to be equal to 0. That is not arbitrary here, these are independent components, that's why it is equal to 0. Yeah, so maybe not the best example. Apology, but did I? Yeah, okay, so the coefficients has to be equal to 0. And one should also point out that, I mean, these are deeper points, that when you have this, like the interpretation is that in going from one, did I change the? So when I go from point 1 to point 2, so you make variations in this, right? That's a understanding we have, that we make a variation and the action goes to 0, but this has to be infinitely tiny variations. It is not true that we can make finite variations and then still the minimization principle holds. So these are all differential statements, exactly like the maximum minima principle in the derivative. It's only the local points that we are capturing. It is not the true maxima or true minima in any way. Yeah, so. Any other questions? Okay. We sort of hinted on where these values will show up, but how do we accommodate the variations in let's say, so that is point going from T1 to T2.
Change the camera.
Oh, yes, thank you very much. So we're going from T1 to T2 and we want to make variations at that point delta R at the boundary. A formal way of doing that is to go back to our action and see that this is not just dependent on R, it is also dependent on T1 and T2. So make the variations in T1 and T2 because we cannot make the variations in time. It is not okay to make the variation in this T, this is dummy. Like this is, I could make T to alpha and nothing is going to change, right? That's a dummy variable. The time dependence is completely in the endpoints, T1 and T2. And we can say when we are talking about change in the action, we can say it is a change in T1 and T2 too. So when we wrote earlier the variation in action, we should say this is delta. So now we are going back to Lagrangian, right? So it is R plus delta R. And now we allow one more variation. It is T1 plus delta T1 and T2 plus delta T2. So that's the total, everything is being varied at this point. Minus T1, T2. That's what we are going to do, and we will see that at this point it is not very clear, but we will see that this amounts to change. We are making the variations at the boundary also. Is that clear what we're doing? So there was an action, it's dependent on T1 and T2. We were not varying that at this point. We make the variations in T1 and T2. If you explicitly wants to see this, it is equal to T1 plus delta T1, T2 plus delta T2. The variation is at the limits, right? So how do we take care of that? This is dt and L, nothing happens to the time is dummy. So R plus, so maybe I should. Yeah, plus delta R, these are implicit variables. And d by dt again. Dt of R plus d by dt delta R, which is implicitly dependent on the time. And there is a t dependence, which is the explicit dependence, and this is all dummy, right? This t, all these are dummy variations happen only on the explicit, I shouldn't say explicit, on the left-hand side variables, the boundary points, and that's T1 plus T2. But we would like this variations to be brought inside the integral. Like if you have a limit, how do you bring it inside? Whenever you have an integral, you can make substitutions. Like we are allowed to make any substitution we want and change the integral. So let's make some substitution. So this is time, right? I want to somehow bring this limit from the, or make this variation in the limits into the integral and leave these limits as it is, T1 and T2. So I'm going to make it click here. Let me make a substitution. T prime is equal to T. So usually we say sine.
There should be another part, is
Another partial what?
like normal, like,
Oh, you mean minus of this?
yeah.
Oh, yes. Thank you. That's what you meant, right?
Yeah.
Correct. R, P, R, I do T
Constant integration.
and T. And what did you say? Constant of integral.
That little part where that little part be like. On the kind of would form like the constant integration.
You mean, no? Confused, maybe. Maybe you have something I'm not getting your point. Yeah, maybe, yeah.
Or the initial condition part.
Initially, no, right, this is, we are not invoking the initial condition at all at this stage, so probably not, yeah. So, like, I mean, this term is there, this has to cancel out this term, right, whenever we subtract out, so we need that term probably. So, okay, if we proceed, so there is, I can make a substitution at this point, so I'll make the following substitution. Notice delta T1 and delta T2 are specific variations in T1 and T2. They're specific values, they're numbers, but arbitrary. It is arbitrary, but they're not functions. But I say that let's have a function. These two are different. So this is a function of T. It's still arbitrary. So I'm making an arbitrary substitution in T. I'm going to replace everywhere I see T, I'm going to replace it with T minus delta T. Yes, and that I'll call it as T prime. So that's going to be my substitution, but I'll put some conditions because I would like this to change somehow in such a way that delta T evaluated at T1 is exactly equal to delta T1. This one. Right? This was a specific value and delta T. So this function is arbitrary up to this extent. It's still arbitrary because this is itself arbitrary, right? Delta T1, delta 2 is arbitrary, but my substitution is invoking that arbitrariness. If I ask what is T prime at T1, so this is equal to at T1. Sorry, T1, let's say T2 plus delta. So at. I should say at here, so at. T1. At T equal to T1. Right. Or how do you say this? When you make a substitution, I have to replace, this is a value for T, right? So this is T. Right, and integral limit is T equal to this and T equal to that. So whenever I put that T, I should get the T prime, so at T equal to T1 plus delta T1. T prime is equal to, I substitute that in there. So T prime is equal to T1 plus delta T1 minus of delta T evaluated at T1 plus delta T1. That's equal to T1 plus delta T1. This is a function expanded minus of delta T evaluated the first variable plus higher orders. I'll write it as plus higher orders. This is a very small quantity. Already it was a very small quantity. Small quantity evaluated at another small quantity, so that's a higher order. These two are the same because this I said is delta T1, so that's cancels out and that's equal to T1. So when I choose this substitution, what it is doing is that this lower limit is exactly T1. So I get back to my original form. But all this T will transform into inside the integral. So that's what is going to happen. Do the same thing at T equal to T2 plus delta T2. And you will get T prime is equal to T2 plus delta T2 minus of delta T evaluated at T2 plus delta T2, and that's the same as T2. And that's T2. What can I tell about dt now? So I have to go each term, right? So now I have done these two in this new term, but now I have to change dt to dt prime. So let's do that. Maybe I can do it here, right? So looking on one page. So t prime is equal to t minus delta t as a function of t. So dt prime will be equal to dt. We are taking a derivative, maybe take a derivative so that it's cleaner. So dt prime over dt, that's equal to 1 minus time derivative of delta t. Of course, the t dependence isn't there, I'm not showing it. So dt prime would be 1 minus variation in time times dt. But I have to replace dt, right? So I would like to replace dt with dt prime. So put it on the left hand side. So dt will be equal to dt prime over 1 minus d by dt of dt prime. But that's not very useful because this is in t, right? I want everything in terms of t prime. So this is not very useful. So let's go back a little bit. So I would like dt prime, right? So let's go back a little bit. Maybe after all, move this way. Take 2 more minutes and I won't be able to too much, but it's just beginning, right? But at least let me finish this. So T prime is equal to T minus delta T as a function of T. I'm interested in the opposite. So let me write T is equal to T prime plus delta T. T. Like this is what you do when you substitute integral substitution, you do, if you're doing substitution one variable with the other, you try to do both sides, right? But again, now there is this T sitting here. I want to change that to T prime. It's T prime plus delta T. T is this again, so put this back. It's kind of a chain, right? It keeps going there. But I can expand this. This is tiny, it's all infinite smell. In the tiny limit, infinitely tiny limit, this is T prime plus delta T. T prime plus higher orders. Like that's the key that allows me to, even though I'm working with arbitrary functions, I'm able to proceed, do a lot of things. Because these are higher orders. So now I have got a function of T as a function of T prime alone. T prime, T prime. Earlier, I had T prime as T and T dependence. Now I found the inverse. So this is the inverse substitution if you want. Like whenever we are doing substitution, we want the inverse. We should be able to come back also. So now do dt over dt prime equal to 1 plus d by dt prime of delta t. So it's basically t prime in here. So I can replace dt with 1 plus d by dt prime. So this is t prime dependence. This is what will go in here. This dt can be replaced with a new term, and now next we have to do derivative between. That's the only place where there is a non-trivial form of t showing up. This t will be easy. We can do that, and we'll come back and do that, and then do the expansion again. And we will learn what we can gain out of this. And this will lead to what is called the Noether's theorem and the conservation principles. How do we know that energy, when is energy conserved, when is momentum, linear momentum? Thank you.